Okay, guys, so this will be our final video for Math 9, and we're going to be talking about the last little bit on probability, which is the part of what your test is going to be on this Friday. So, anyways, I want to say good for you guys for hanging in there. I know it's been a tough go doing this Zoom chatting thing, and also the video recordings. So hopefully next year we're going to have a bit of a hybrid model where we'll be in the building more often with you guys, and having unfortunately do some of this video stuff still, but hopefully a lot less and more time with students to talk about the questions you're working on and talking about or teaching you the lesson more in person, which I always think is better. So so good on for you guys for hanging in there, and just one more test, and then of course the optional final if you choose to do that. And I will be sending an email about that soon, so please keep scanning that if it's something you want to do. Okay, so I'm going to talk about, actually before I go to the OneNote there, just a little bit about what we call events occurring. So for example, if you flip a coin, then you can get heads or tails on the coin, and basically getting a heads is one event, or there we go, heads is one event, and a tails is the other event. If you take a deck of cards, and you have 52 cards in the deck, all these, cool, that's a backwards card there. Jack of diamonds. And so you take all these cards and you draw one of these cards and you say, what's the chance of me getting a heart? No, loser. And anyway, so the chance of getting something, an event would be what you're looking for. So getting a heart would be an event you're looking for. Now, there's lots of events you may not be looking for. And of course, if there's lots of those, then your chance of getting the event you want is probably reduced. So if I want to get a tails on this coin, my chances are better than if I wanted to get, say, the Jack of diamonds on one cut of the deck. Jack of diamonds, Jack of diamonds. No. Okay. Oh, what about that? Oh, Jack of diamonds. Sorry. So anyway, so there's some examples of events, and then you got dice. So you can have like an 8-sided dice or 12-sided dice, or your standard 6-sided dice. And you might be asked questions about rolling a dice and saying, what's the chance of getting a 3 on this dice if you rolled it, or what's the chance of getting a 2 on this dice here? And so that, once again, those are events from each other. And so today's lesson is sort of looking at the two kinds of events that I want to talk about in this course, which are dependent events and what we call independent events. I'm going to be writing a lot of this down, but I just wanted to go, I wanted to be able to see me first, and then I can show you with dice and coins and things like that, what I mean by that. So for example, if you were to roll a 6-sided dice twice, so if you rolled this dice twice, and let's say the first time you rolled it, I roll it, and I got a 6 actually. So let's say you get a 6. And now I roll it again. So I roll it a second time, and I just told you we got a 6. And I ask, what's the chance I get a 6 when I roll it again? So does it matter that I got a 6 the first time, or does it not matter? Does it make a difference, sort of thing? So I roll the dice the first time and I get a 6, and the question is, what's the chance if I roll it again, I'm going to get a 6 again? Or let's say you flip a coin, you flip this coin 10 times, and you get like heads, tails, heads, tails, heads, tails, and a combination of things. But let's say you got, on the last 3 flips, you got a heads, and heads. Okay, so that happened. And then I flip it now, and I say, what's the chance I'm going to get another heads? Does that change? Does it change on the fact that you actually got these 3 other heads in the beginning? Or let's take a deck of cards. A lot of things to remember here. So you can always rewind the video if you're not sure. So I got the dice question, the coin question, and let's just look at cards here. And let's say that you have your standard deck of cards here. Okay, so deck of cards, okay. Club right there, but I'm going to cut it now so that you can't see what's on the bottom, okay. Let's just say I shuffle it all up. So now you don't know where any of the cards are, okay. And what I'm going to do is I'm going to take the top card here, and I'm going to put it down, okay. And I'm going to take another card and put it down, okay. Okay, so I've taken 2 cards, okay. And I'm going to hold them up in the order in which I drew them. So I'm not going to show you. So this was the first card I picked, and this was the second card I picked. Okay. And let's say I ask the question, what's the chance that this card, the second card I picked, is a diamond? So what's the chance that this is a diamond? So once again, this was the first card picked. This was the second card picked. Okay. So does it matter? Does it matter what this card is? Does this have any changing effect on this card, the second card picked here? Or what if I said to you, this is the first card, this is the second card. What's the chance this card is a diamond? Would it be the same as the chance of this card being a diamond? Okay, so I'm going to draw this out for you guys to show you, but I want to just go over those two words again we talked about, which was dependent events and independent events. So to be independent, like right now, you guys are dependent on your parents. Like you depend on them to, generally speaking. Some of you guys might be going it alone right now. I hope not. That's tough go for a young person. But generally speaking, your parents, they buy the food, they provide the house for you to live in. They do a lot of things for you, and although as a teenager you may not appreciate any of those things, I shouldn't say that, but you may or may not. But as you get older, at some point you're going to move out, or your parents are going to kick you out and say, "Get out of here." And you're going to have to become dependent, and so you're going to have to take care. Sorry, independent. I should say you're going to have to become independent, which means you're going to have to take care of yourself. Okay, so I like to think of it that way first. And so when I roll the dice, if I rolled a 6 the first time, and now I go roll it again, does this second roll depend on what I got the first time? Or is it independent? Does it matter? Okay. And the answer to that is it's independent. There's no way rolling a 6, even if I rolled 10 sixes in a row, and then I pick up the dice and I roll it again, and I want to know what's the chance I'm going to get a 6 here. That is not dependent on what happened before it. So that is an independent thing. Now, what would change the meaning of this question, the way I worded it, was if I said to you, what's the chance if you roll this dice 10 times and all 10 times it's a 6? Now, each event would still be independent, because it doesn't matter what you rolled before, but the likelihood of that would be very low. And so I think sometimes in our heads we think, well, if it's a low chance, then somehow that must impact what has happened before. But rolling a dice, every time you roll this dice, assuming it's a trick, not a trick dice where it's weighted in a certain way, it rolls a certain number all the time. If it's a fair die, I should use the word die, it's a singular. So if I roll this die, then every time I roll it, there should be a 1 in 6 chance of getting whatever numbers are on the surface here. If I roll a 12-sided die, it should be a 1 in 12 chance of getting any one of the numbers on this die here. And if I rolled an 8-sided die, same thing, 1 in 8 chance of getting any one of those numbers. And of course, you could roll a 4-sided die. I got a big Dungeons and Dragons game coming up today. Just kidding. But of course, you get a 1 in 4 chance of rolling any one of the numbers on here. And what about the coin? What about the coin question? Well, the coin has 2 sides to it. Now, technically, I was in class earlier this week, and one of my students very smartly and astutely said, "No, there is not 2 sides to a coin," and she was right. There's actually 3 sides to a coin, because you have it's a cylinder, right? So you have front and back, heads and tails, and you got an edge piece right here. But when we flip the coin, because it's rotating, when it lands, assuming it lands on a nice smooth surface, it'll always sort of fall to one side or the other, or unless it's propped up against a wall or something. So generally, we associate there's a 1 in 2 chance of getting a heads or a tails on the coin here. Okay. And now the card question. So flipping a coin is independent events here. And then the card question. Now, I said this was the first card. This was the second card. This card being a diamond, although there's 13 diamonds in a deck of cards, you might say, well, it's a 13 out of 52 chance. But because it's the second card picked, if I had picked a diamond, well, now there wouldn't be 13 diamonds left. There's going to be 12. So this card does actually, the probability does depend on what actually happened here. And if this wasn't a diamond, then this would be 13. But what's weird is there wouldn't be 52 cards in the deck now, because if I picked this card first, there's only 51 cards in the deck now. So this probability actually does change depending on what happened here, what this is, but also whether you replaced cards or not in the deck. So if you did a question where you drew a card and you looked at it, so I look at this card, and then I put it back in the deck and I shuffle it, and then I draw a second card, well, now there's 52 cards back in this deck, so it's something out of 52, whatever it is. But if I draw a card and don't replace it, well, now there's only 51 cards in here, which means if I draw this one, this is whatever the chances of this occurring, there's a number of these things, divide by 51 cards then. So this independent and dependent events is tricky, because you got to think, does something you did before, could it impact the outcome of what you're looking for? So with cards, if you draw cards from a deck of cards and you don't replace them, then every time you do that, you're changing the number of possible total number of things that are in this thing here. But when you roll a coin, if you flip a coin or you roll a dice, so if you flip a coin and roll a dice, then these events are independent, because it's not like when you roll a 6, the 6 disappears. It's still a 6 on that dice. So whenever you roll, there's still a 1/6 chance of getting any one of the numbers on this die. And then flipping a coin, it's like if you flip a coin and get a tails, it's not like the tails goes away now, and now there's no tails. There's still heads and tails on the coin. So I'm going to draw some tree diagrams here and talk about this kind of math. And I hope this kind of showing you some stuff visually helps you kind of see it, because it can be a bit abstract, this probability thing. So really the video is going to focus primarily on independent and dependent events. So try to remember about, the idea that you guys are dependent. You depend on parents right now, generally speaking. You're becoming more independent. Like you're definitely much more independent than you are when you were like a little baby or something like that, where you couldn't even stand up. So as you get older, you become more independent, and then at some point you will become pretty much completely independent and taking care of yourself. And then right now you're kind of in that quasi state where you're fairly independent, but still dependent on some things. Okay, so let's take a look here. So let's switch over. Hopefully that wasn't too much rambling. So let's take a look at a specific question where we can actually work out the probability. And I'm going to work out the probability in 3 different ways. One is writing it as a fraction, and then the other would be writing it as a decimal, and then the third way would be writing it as a percentage. The most common way in probability is actually a decimal form, but fractions are quite common too. And actually, funny enough, percentages aren't the most most common way we write them out in terms of probability. So let's take a look at a question involving, let's do a coin first here, okay? So let's say the probability of flipping a coin, and you want to know probability of, let's say you flip it twice, okay? And the probability of getting 2 tails. Okay. Now I did do a little bit of this on the Zoom meeting yesterday, so I'm going to kind of repeat myself a little bit here, but I think it's good to do that just to show you how we use basic tree diagram to answer questions like this. So the homework sheet does talk about going through a tree diagram here. So the first branch is what could happen the first time you flip the coin. So the first flip could be heads. I'll just use H for heads and T for tails. And there's a 1 in 2 chance of either one of those occurring. Okay, and then the second flip, you could, if you got a heads the first time, you could get a heads the second time or a tails. And if you got a tails the first time, you could get a heads or a tails. So there is actually different branches that could occur here, and each one of those branches is 1/2. Okay, and then the question is now, well, which branch shows the probability we want, the favorable outcomes? So we want to get two tails. So what I'm looking for is the tree branch that ends with 2 tails. So this would be a tails on the first flip and a tails on the second flip. So that would be 2 tails. So what I do is I multiply the branches. So each branch times the probability. So 1/2 times 1/2 is 1/4. Okay.
Now I could say the probability, if I was to say equals, so the probability of two tails would be 1/4. As a decimal, that's 0.25. And if I want to convert it to a percentage, I would times it by 100, because that's how we convert to percentages. So that would be 25%. So it's 25% chance, 0.25 probability, or 1/4 probability of that occurring. Okay. Okay, so that's our coin question. Let's try one where we're looking at, let's say there's more than those two outcomes on the coin. So let's use a dice here, okay? And let's just use a standard 6-sided dice here. So what's the probability if let's say you rolled a dice twice, the probability that you got a 3. So the probability you rolled a 3 both times. So let me write that differently. Let's say you rolled both numbers are 3. Okay, so that you rolled a 3 the first time and a 3 the second time. Now, if you do a tree diagram, there's two ways to do the tree diagram. One is really going to take a long time, and I'm going to just show you really quickly, or I'm going to erase it pretty fast because it's just terrifying. So you could say, well, what could happen? So you could go 1, 2, 3, 4, 5, 6. And so those are the 6 things that could happen when you roll a 6-sided dice. And then, of course, let's say you got a 1 on the first roll. Well, then you could get a 1, a 2, a 3, a 4, a 5, a 6. 1, 2, 3, 4, 5, 6. And you can tell if I keep doing this is going to take literally a long time. Okay, so I'm gonna not do it that way, because I think that way is just really tedious. And what I'm going to look at is the event I want to occur. So the first roll, I would want to get a 3. Okay, so I need getting a 3 on the first roll. And then what else could happen? Well, I guess I could not get a 3. And so what I do with my tree diagrams, I kind of make it look like the coin question now. But what you'll notice is it won't be 1/2, 1/2, because if you're rolling a 6-sided dice, there's 6 outcomes that could occur. And getting a 3 is only one of those outcomes. And of course, if you don't want to get a 3, that means you could get a 1, a 2, a 4, a 5, right? I think I missed something there. Sorry, and a 6. Sorry, yes, and 6-sided dice. So there's 5 other outcomes that could happen that are not 3s. And so by doing this, the tree diagram gets a bit smaller, and it's less lines that I have to draw out here. So I would encourage you to do that. Otherwise, there are a few questions that are going to take you like a long time. Like imagine doing a deck of cards, and you're like, "What's the chance I get a queen?" And you're going to draw 52 lines. Like that would be very painful. Okay, so if you want to get a 3 the first time, then you could get a 3 the next time, or not a 3. A 3 and not a 3. Okay, so I'm just looking at doing 2 rolls of the dice. So these are all the things that could happen here. And then now if I roll a 3 the first time, the chance of me rolling a 3 the second time, does that change? That is, does somehow getting that 3 the first time, is it like some kind of effect that prevents 3s from being rolled in the future? Well, no, a dice still has 6 sides. So 1 and 6, 5 and 6, 1 and 6, 5 and 6. And so we refer to these as independent events. So the idea of rolling 2 3s, they are independent of each other. The second 3 does not depend on what the first roll was. So once again, look at the branch that shows you getting 2 3s. So there's 1 3, there's 2 3s, second roll. And so what I do now is I times my numbers together. So I have 1 6 times 1 6. So 1 times 1 is 1 out of 36. So that is a probability equal to 1 over 36. And if I convert it to a decimal, it's not as easy, obviously, as the other question. So 1 divided by 36, it's about 0.028, roughly, which means about a 2.8% chance to have that occur. Okay, So once again, if you're going from decimal numbers to percentages, you just times it by 100%. So getting 2 3s and 2 rolls of a dice is very, very unlikely. We asked that question earlier in the video about imagine rolling it 10 times in a row and getting 3 10s in a row. Would that be very likely? Well, no, because that would actually be 1 6 times 1 6 times 1 6, like doing that 10 times. So you'd have like 1/6 to the 10, which would be, well, you can use your calculator for that. It's not very good. Okay, so that's independent events. Okay, so let's take a look at a question we haven't shown you yet. Let's take a bag of marbles. It's kind of a question that's quite common in probability courses. And let's say you have this bag here, and have a little rope around it. And inside the bag, let's say I'll keep the numbers sort of small here. Let's say you've got 3 green marbles. Okay. 1, let's say 2 purple marbles. Okay. And let's go for 1 orange marble. Okay, so you got 1 orange, 2 purple, and 3 green. And let's say, just like the other questions, we're going to do 2 trials here. So we're going to reach into the bag, and we're going to pull out a marble, and then we're going to pull out another marble. And then for the first one, what I'm going to look at is what we call with replacement. Okay. Now what that means is you pull out the marble the first time, you look at it, and then you put it back into the bag. So we're going to replace it, and then you draw a second marble. Okay, and then look at that. Okay, so you're drawing 2 marbles, but you do it like 1 at a time. And after you've picked the first marble, you just put it back in the bag, you mix it up again, and you draw a second marble. Okay, and the question is, let's say, what is the probability of getting the first marble being red, or sorry, being green? First marble is green, and second marble is orange. Kind of running out of room here. Okay, hope I squeezed that in enough. Okay, so once again, I'm going to use a tree diagram. It's kind of what we're trying to teach here. So the main lesson here is tree diagrams, actually, and not about marbles and dice and stuff. Okay, so what do we want to have happen? Well, I need the first marble to be green. Okay. Now I could do 3 branches, and make these like purple and orange, right? I could do that, but really I want my first marble to be green. So really, I just want the other thing here to be the not green marble, right? So I'm gonna erase my 3rd branch and not write purple, but write let's see, write not green. So that would mean basically the purple and the orange. Okay. But if you want to do 3 branches, you can. It's up to you. Okay. So if you reach into this bag, well, how many things could happen? I mean, like, how many outcomes are possible? Well, there's 3 green, 2 purple, 1 orange. So there's 6 marbles in the bag. So it's almost like a dice question. So you've got 6 things that could happen. And then if you want a green marble, how many things are green? That is, how many things could you have grabbed that would be green here? And so there's 3. So really, there's a 1/2 chance of that occurring. And if you could grab a purple or an orange, then there's 2 purple and 1 orange. So there's a 3 in 6 chance of that occurring. Okay. Now the second marble, I want to be orange. Okay. So I'm going to look at orange and not orange. So that would be purple and green, and orange and not orange. Okay. So what did we do with that first marble? Well, we put it back into the bag. So basically on the second draw, there's still 6 marbles in the bag. And then how many orange marbles would be in the bag? Well, 1 orange marble. So it'd be 1 in 6 chance of that occurring. And even if you pick the not green one, you're still returning it back to the bag. So there's still 6 marbles. So still 1 in 6 of getting the orange. And of course, not getting orange, well, you got 3 green and 2 purple. So 5 out of 6. And then 5 out of 6. Okay, so once again on the test, we're going to want you to show a tree diagram. So that's what a tree diagram looks like. And now we look for the outcome where we have a green, and we have an orange. Okay, so we take those two branches and we multiply the numbers together. Now, if you want to reduce the 3 over 6 to 1/2, that's probably going to make it easier for you for the math, but I'm not going to do that right now, just to show you that it still gives you the same answer. So 3 over 6 times 1 over 6 would be 3 out of 36. So the answer would be 3 out of 36, but we know to reduce that. We're Math 9 students now, right? So we're able to handle fractions. So that would be 1 out of 12. So there's a 1/12 chance of that occurring. And then if I turn that to a decimal, 1 divided by 12, so it's a bit better than the last question, not much though, 0.083, which is about 8.3%. So once again, we're kind of wanting to show all three versions of the way to write that, okay? Fraction form, decimal form, and percentage form. Okay, so let's do a question where we have without replacement. Okay, so without replacement. So I'm gonna go down here and I'm gonna change the color I worked with. So let's use, what color have I not used yet? Let's use orange. That's pretty cool. So let's say without replacement. So what does that mean? Well, that would mean that you pull your first marble out and you look at it, and then you don't put it back into the bag. So you keep it out. And then you reach in again and you grab a second marble from what's remaining in the bag and look at that one. So what happens here is you're changing the number of items that are actually in the bag itself, okay? So I'm gonna take a look at the question of what's the probability of getting 2 green marbles? Okay, so that means the first time you reach in, you get a green marble, you don't replace it, you reach back in again, and then the second marble you pull out is also green. Okay, so once again, tree diagram here. So let's do our tree diagram. So we go what we want first of all. So I'm gonna go green and not green, green and not green, green and not green. Okay, so there's all the outcomes that could occur here. Okay, so let's take a look at that first choice here. So you reach in to that bag, you pull out a green marble. For green marbles, there's 3 of them, right? So there would be a 3 and 6 chance. So that's actually kind of the same as the last question, right? Because we said we want the first one to be green, and then 3 out of 6. Now the second time we do this, we don't replace the first marble. So that would mean there's not 6 marbles in the bag. There would be 6 minus 1 is 5. So we'd have something over 5, and then we would have something over 5, okay? And then something over 5, and something over, only 5 marbles left in the bag. Now, if you had pulled a green marble out, there would be 1 less green marble, so that would be 2. So that would be a 2/5 chance. And if you had pulled a green out, there would actually be 3 other marbles that are not green. That'd be 2 purples and an orange. So this would be 3 out of 5. Now, although I don't need to do the other branch for this specific question, I'm going to do it anyway because when you're in higher grades, you might get a question like, what's the chance the second marble is green? And so we'll talk about just the tree, how that looks. But if you didn't pull a green marble out, that means there'd still be 3 green marbles left in the bag. So really this would not be 2, this would be a 3 here. Because remember, there'd be 3 green marbles because you would have taken one of the orange or purple ones out. And of course, if you took one of the orange and purple ones out, there'd be 2 non-green marbles. So notice, I'm just going to just highlight this. You don't need to know this for Math 9, but notice that this number is different than that number. And we'll talk about the meaning of that in a second here. But for this question, what we want to know is getting 2 green marbles. So there's the only branch that shows green and green. So I times these numbers together, and once again, if you reduce it, it does make it a bit easier to times. So 1/5. But if you don't reduce it, you get 6 over 30, okay? Which is the same as 1/5. So the chance of getting 2 green marbles is 1/5, 1 out of 5, that's a chance. And that is going to be 0.20 as a decimal number, and would be 20% chance of that occurring. So pretty pretty good chance. Not great, but much better than the other questions we've done. Okay, so let's go back to that big thing I was talking about, being dependent and independent here. So really the first question, this one up here, that's an example of where you replace the marble back into the bag. And so we would say that these events are independent of each other. So the second event right here of getting an orange, it really doesn't matter what you got the first time because you put the marbles back in the bag. So there's no change on the number of items there and how many of the ones you would want. However, the second question, notice how the probability changed here because you did not replace the marble. So we would say that if you don't replace it, this is an example of dependent events. And notice that this number here, 2/5, is actually different than 3/5. And the reason it's different is it depends on what you got the first time. If you got a green, it's 2/5 chance of getting another green. But if you didn't get a green, it's a 3/5 chance of getting that. So so really that is different than that, right? So independent means does not matter what happens the second time, whereas dependent, it does matter what happened the second event does not. I'm going to go back to independent, sorry. For independent, the second event does not depend on what happened before. But for dependent events, the probability of the second event does depend on what happened before. Okay, so I'm going to do one more question with cards. There's a card question on the sheet here. And so there's a little blurb on what's really in a deck of cards. So if you're not sure, I've written that out for you. I've also shown what a deck of cards has in it. So if you're not familiar with a deck of cards, the sheet of paper will show you that. So let's do our last example here. Okay. So example would be, let's say you draw 2 cards from a deck of cards. Okay. So you're gonna pick a card and then pick another card, and we're gonna do this without replacement. Okay, so no replacement here. Okay, so you draw a card, you keep it out of the deck, and you reach in and draw another card. And the question is going to be determine the probability of getting a jack. So the first card is a jack first, and a king second. Okay, so without replacement, that means that the second time you draw a card, there's going to be fewer cards in the deck. So this is going to be an example of a dependent event. Okay, but let's draw a tree diagram here. Now, once again, if you draw like literally all the branches that could exist here, it's going to take you forever, right? Because you could have jacks, you could have kings, you could have aces, you could have twos. It's going to take you forever. Actually, that's not true. Not forever. It's just going to take you a longer time. So I'm gonna write jack and no jack. Okay. Now my second card, I want to be a king and no king and king and no king. Okay, so what you would need to know though about cards, like what kind of cards are in a deck, and once again, the sheet of paper does show this. If you're kind of like, I didn't know that, that's okay. There are 4 jacks in a deck of cards, and there are 4 kings in a deck of cards, and there are 52 cards in a deck of cards. Okay, so really for the first question, you would have 4 out of 52. Okay, which actually is 1 out of 13, but I'm going to keep it as 4 out of 52. And then for no jacks, well, basically 52 minus 4 would be 48 other cards that are not jacks, divided by 52. Okay. Now, if you pulled a jack out and you didn't replace it, so you didn't put it back in the deck, would that change the number of kings that are in the deck? So you took this card out that's a jack. Would there still be 4 kings in the deck? Well, of course, there'd still be 4 kings. But there would only be 51 cards in the deck now. So that bottom number changes because of the no replacement. And of course, for no kings, You have 51 cards, but remember you've already taken the jack out, so you still have 51 cards, and that would be 47 then. Okay, so there'd be 47 cards that are not kings in the deck. And let's say you didn't pick a jack, there would be 51 cards, right? There'd be 51 cards. But I think what would be the problem is you wouldn't know what that number is yet. Because if it had been a king, then there'd only be 3 kings left, so 3 out of 51. But let's say it wasn't a king, well then there'd be 4. So if you were trying to find out this branch, or maybe this branch, you would actually have to know a bit more here. So you might want to create a third branch at the top that talks about kings. But that's beyond the scope of what I want to test you guys on, okay? So what I want to look at is the chance of getting a jack the first time. There's a jack. And then getting a king on the second time. So that's that branch there. So that would be 4 out of 52 multiplied by 4 out of 51, okay? Now we can reduce the first number to 1 out of 13 multiplied by 4 over 51, but that's as far as we can go. So if I times that, that's going to be 4 out of 13 times, 13 times 51, which means 4 out of 663, which is a very small number, which is 0.006 roughly. Okay, and if I times that by 100, I get a 0.6% chance of that occurring. Lots of cards, obviously, in a deck of cards. Okay, so that's where we're going to end the video off there. Big thing today was tree diagrams. So that's really what you're going to be asked quite a bit on your test is tree diagrams. And we talked a little bit about dependent events. So those are ones that depend on what happened before. So flipping coins, they're not dependent. Rolling dice, they're not dependent. But taking cards from a deck of cards where you're not replacing them, that would be examples of dependent events. And then we have independent events, which are ones in which what happened before does not matter to the second event. So that would mean like flipping a coin, the chance of you getting heads or tails doesn't matter, doesn't depend on what happened before. Or rolling a dice, they are not considered to be dependent, they're independent events. Okay, so I hope that answers your questions, and the worksheet on the Google Classroom will deal with these kinds of questions. Okay, so take care. Where are we here? Yes, so take care, and we'll maybe see you next year, maybe in Math 10, or maybe a couple of years from now in Math 11 or 12. Okay, take care, guys. See ya.